Before we jump into alcohol reactions, let's do a quick overview so that we're on the same page with this molecule. An alcohol is a molecule that has a functional group with an O and an H. And specifically, we're looking at just an OH, an alcohol like this. I don't want you to confuse it with something like a carboxylic acid. The carboxy has an OH, but it also has a carbonyl on that same carbon that is not an alcohol. We're looking for just an OH by itself. When you're naming an alcohol as the highest priority functional group, the suffix, the ending of the name will be OL. For example, the molecule that I showed you right here will number it from the left, giving me 4 carbons for a 2-butanol, where the alcohol shows up on carbon number 2. In order to go through the alcohol reactions, we need to understand how to classify the primary, secondary, and tertiary alcohols. And to do that, we're going to use the pencil trick. So let's draw a really big, complicated molecule over here, and we'll add a couple of alcohols to it. So we'll have one right here. We'll have another one here. And we'll add one more alcohol right here. What we're looking for to classify these alcohols is to see how many carbons the carbon holding the alcohol is attached to. So let's try that again. We look for the alcohol. We look at the carbon holding that alcohol, and then we see how many other carbons are attached to that. And the reason I call it the pencil trick is because if I take my pen or pencil and I put it there, I simply draw a line from that carbon, the one holding the alcohol, to any carbons nearby. And this one right here, you'll notice, has 2 lines to carbon, making this a secondary alcohol. This one right here has 3 lines to carbon, making it a tertiary alcohol. And this one right here, I meant to do that in green, only has 1 line to carbon, making that a primary alcohol. This will be critical when we're looking at some advanced topics where we're trying to specifically come up with the primary, secondary, or tertiary, as well as some of the mechanisms. If you are just joining or watching the recording, welcome. For a copy of today's session notes, practice, and more, go to leahforsyth.com/orgolive or see the pinned comment, and I will send it right to your inbox. We have the alcohol. Now we need to know how to make the alcohol, because in synthesis, you may be asked specifically for the alcohol or asked for something that has an alcohol as an intermediate where you have to go from a molecule to the alcohol to the next thing. Back in Organic Chemistry 1, you learned the substitution reaction, where you saw specifically the SN1 and the SN2. What specifically categorizes the SN1 or the SN2 reaction? If we have something like an alkyl halide, that is a carbon chain that has a leaving group that is a halogen, for example, bromine, a pretty good leaving group. If I substitute the leaving group for an alcohol, that would be a substitution reaction. Thank you, Jacob. Appreciate that. I can do this through SN1 or SN2, where the key difference, the way that you recognize these reactions, is by the mechanism or the intermediate. With a product, you can sometimes tell, but for example, what I just gave you now, this can undergo both SN1 and SN2, and I'm going to show you both. If the leaving group leaves by itself, and I'm left with a carbocation intermediate, which reaction is this right here? Where in the final step, I will have something like an OH minus come in, attack at the carbocation position, and give me an alcohol exactly where the leaving group used to be. The key here is the fact that I have a carbocation intermediate. The carbocation only shows up with an SN1 reaction, never, ever, ever in an SN2. So this right here is my SN1 reaction. If I want to do this faster, in a more controlled way, assuming I don't have too much steric hindrance, where in a secondary leaving group, this is possible. I can bring that. Oh, I should not have shown that. One more. Let me redo that real quick. So if we have a carbocation, you're not going to see the OH minus. You'll see the conjugate version of that, the weaker nucleophile, which will give me an OH2 plus. And then in the last step, we have to do minus H plus. That is how we get the final product. So there's actually one more step in there. But if I do a direct attack where I bring in an OH minus to a molecule that still has the halogen, still has the leaving group attached, this will happen as a backside attack. Bromine gets kicked out. The molecule, the OH minus, does not wait for bromine to leave. It gets kicked out, and that gives me, in one single step, two molecules reacting at the same time, a bimolecular reaction. The two reacting at the same time is how I know that this is an SN2 reaction. A quick tip to help you remember here is there are no intermediates in an SN2 reaction, because this is a very, very fast reaction, where SN1 is a very slow reaction. Okay. Any questions on substitution? Go ahead and type it in. Another way that you learned how to form an alcohol in Organic Chemistry 1 was with an alkene addition reaction. If I have an alkene, let's start with something that looks like this. I can react this alkene with 3 different reagents to get 3 different alcohols. And this is really, really important, because coming up with the molecule in question is not just about what you're trying to create. It's also about where you're trying to create it. Meaning, do I want my functional group here, here, or here? And so in a situation like this, I will show you all 3 reactions at the same time so that we can compare and contrast and understand what is going on. Using this same starting molecule, the key here that I want you to recognize is that the alkene is situated between a primary and a secondary carbon. Primary because it only has 1 other carbon attached to it. Secondary has 2 other carbons. And then the carbon next to it is tertiary. The reason this is very, very important is because of a rule that I teach you in one of my carbocation videos as follows. Anytime I form a secondary carbocation near a tertiary carbon, you're going to have a hydride shift, a carbocation rearrangement to give us the more stable, more substituted carbocation intermediate for a product that is completely unexpected. So with that in mind, let's start with the standard acid catalyzed hydration using H2SO4, our acid catalyst, in an aqueous solution, a mild acid catalyst, in this case, H2SO4 in water. The mechanism, if you'll remember from Organic Chemistry 1, had a carbocation intermediate where the pi bond reached for the H+. The carbocation formed at the secondary, more substituted carbon. But because the carbocation formed at a secondary position next to a tertiary carbon, there was a hydride shift, a carbocation intermediate, and the unexpected product has the alcohol not on the primary position, not on the secondary where the pi bond used to be. Instead, the alcohol winds up at the tertiary position, the most substituted carbon, even though the pi bond was never there. So I'll put a note here so that you have it. Acid catalyzed hydration. And this is a reaction that has a hydride shift and follows Markovnikov's rule. So I'll put another note for you here. A carbocation shift from secondary to tertiary. This way, when you sign up for the notes, you'll have all of this in one place. If we want a reaction that will give us the alcohol at the more substituted position, we want the alcohol right here, but we don't want the alcohol to move. We want it to stay at the secondary position. We want to use the reaction that I call the carbocation babysitter. Give me Markovnikov's rule, but babysit that group. Do not let it go anywhere. That is the oxymercuration reaction. If we use something like HgOAc2 in an aqueous solution for step 1, and follow up with a reduction using NaBH4, the alcohol will form at the more substituted carbon because it does follow Markovnikov's rule, but the mercury intermediate will hold on to that carbon, will not allow the carbocation rearrangement to happen, and the alcohol winds up at the secondary position, the Markovnikov's rule. So this is oxymercuration, and it follows Markovnikov's rule, which I will write as Mark's rule because his name is way too long to write out over and over. So that gives me the second reaction. The third one is if I want my alcohol at the primary position, and this will be critical when you're doing synthesis and you want, say, an ether, or you want to create a longer chain, but you need that alcohol or whatever the alcohol is going to give you at the terminus, at the end of the molecule. You want to use the reaction that will go anti-Markovnikov, and that is the hydroboration reaction. For hydroboration, we're going to start with BH3, not BH4, getting ahead of myself there. We're going to use BH3 in THF as step 1. Step 2, we'll use NaOH, H2O2, and some professors will also have you add H2O. This is an anti-Markovnikov reaction. It does not have a carbocation intermediate, and so the alcohol winds up at the primary position because it's an anti-Markovnikov reaction. So we have one starting molecule, 3 unique products. If you find this helpful, seeing them all together, so that when you have to do this in synthesis, you now know where to choose. I want to see a heart or a thumbs up in the comments. If you are watching the recording, let me know if you're already working on synthesis with alcohols so that I can catch up on the comments after. I see hearts coming in. Excellent. And a question. Where does bromine leaving to? So let's go back. You're asking about this question. In both situations, bromine as a leaving group just gets kicked out and dissipates somewhere into solution. So it'll dissolve and remain there as a spectator ion, meaning something that is happy, stable, and no longer reactive. So this is a summary of the alcohol formation reactions that you covered in Organic Chemistry 1. Now let's move on to some of the more advanced reactions that you're going to learn. Actually, before we do that, let's talk about reversing the reactions. Because what if instead of asking you to create the alcohol, you're asked to start with an alcohol and get rid of it? So reversing the above reactions, we will start with, well, let's use this alcohol. And because the first one I showed you was with a halogen, how do we get that halogen back? If you look back to the reaction itself that we did before, in both situations, bromine was a good leaving group. Once it left, it was stable, it was unreactive, it didn't bother us in any way. But if we want to reverse the reaction, and we try to get alcohol to leave, unlike bromine that formed a stable bromide in solution, if I try to create something like this, is this going to happen? Is this going to form? No. Alcohol is a very, very bad leaving group. It does not want to leave. And so the moment you manage to somehow, I don't know how you manage to kick it out, it will immediately turn back around and attack. It does not want to leave. It's terrified. It's not stable on its own. So what we have to do in a situation like this is you have to take alcohol that is a bad leaving group and turn it into a good leaving group. Option number one is to bribe it. And the way you can bribe it is actually with multiple different options. So bribe number one is to protonate. So let me show you what that looks like. If I take the starting molecule that I had before with an OH, and I react it with a strong acid like HBr. In a situation like this, the alcohol being greedy, the oxygen is highly electronegative. It reaches for that hydrogen, kicks out the bromine, and what I have now is instead of an OH, which is a bad leaving group, I have an oxonium, an OH2 lone pair positive charge. Now, if this molecule were to leave, I get a very stable carbocation, well, a stable enough carbocation, but I also get a water molecule in solution that is way more stable than an OH minus in solution. And that water molecule is the green oxygen, the green hydrogen, and that purple hydrogen, neutral, happy. So that is one way to get rid of the alcohol. From this carbocation, I have two options in terms of where I'm going to go. Option number one, in the case of having bromine, the Br minus in solution, even though it's not very reactive, it is opportunistic. And in a situation like this, it can very well turn around and attack the carbocation to give me an alkyl halide as one option. Now, something like this is not typically ideal because bromine is not very reactive. It depends on the degree of substitution, meaning how substituted that carbocation is. And so the other option you want to consider for bribing your carbon chain to get rid of the alcohol is to use a molecule that will make it much more stable. For example, if I have an OH, and I react it with something like PBr3, then this molecule will get attacked. The alcohol will attack it, give me a big, bulky leaving group that will ultimately get kicked out. And then what I'm left with is just a bromine. And the rest of the molecule on the side, in this case, will be H3, PO3, but you don't have to worry about that, or you may not have to worry about that. A couple more that you're going to see is, for example, if I take this alcohol and this time I react it with SOCl2, you're going to see this a lot in Orgo 2. Pyridine is a good mild base, great for stabilizing any acid that forms. And that will give me the chlorine is going to add. So notice that this one had a bromine. I added a bromine. If I want a chlorine, I use SOCl2. And that means I will then have just a chlorine plus I'll get SO2. I'll get a mild HCl. And the reason I can show this is because the pyridine is going to balance it. Another one you're going to see with chlorine is, and you've probably seen this one more frequently, is reacting it with a tosyl chloride. The tosyl chloride is para-toluene sulfonyl chloride. Let me know in the comments if you are taking the ACS this semester, because if you're taking the ACS, you do have to know what the structure looks like. And this, once again, will give me a chlorine in place of the alcohol. Aaliyah, we can, and Quanta is taking the ACS, so you definitely have to know what this looks like. If you have any questions so far on what we discussed, go ahead and type it in. In the meantime, let's move on. Actually, I didn't finish showing you. So we have, these are all for reforming the alkyl halide. These would be substitution type reactions because I substituted the OH. If I want to reform the alkene, let's go back to the alkyl halide. And I don't know why I keep using bromine today. You can also see this with chlorine, with iodine. If I want to reverse the acid catalyzed hydration specifically, I want to use, again, H2SO4, but this time I want to make it hot and concentrated because heat, if you remember, favors elimination over substitution. And in this case, when I have a carbocation intermediate, so remember the chlorine is going to leave by itself, I have a carbocation. Instead of the water molecule coming in and attacking here, the water molecule is going to grab the more substituted beta hydrogen. And in doing so, we will form a pi bond, or in this case, reform the pi bond because we're trying to reform our alkene. Grab the hydrogen, give the electrons back that collapse upward in the direction of the carbocation. And that is how we reform an alkene from an alcohol. So now that we know how to reverse the reactions that we just covered, let's move on to the next topic that you will have done in this chapter, probably the first one you did in Organic Chemistry 2, and that is redox. So we're going to start with oxidation of alcohols, and then we'll look at the reduction of alcohols. There are many, many different mnemonics that you will have learned. My favorite to use is the following. And let me know if you learned this one or something else. And the mnemonic here is Leo the lion says, grrr. That's my scary grrr growl. What that stands for is loss of electrons, oxidation, and gain of electrons, reduction. Before we continue, I see some questions. So all of them will just replace the OH with a Br and a Cl, yes. And the reason this is so important for synthesis is you start out with an alcohol, but you need something completely different. Maybe you're trying to turn it into a Grignard. Maybe you're trying to turn it into a longer chain where you're going to have an attack and you need that alcohol to be a leaving group. So you first turn the alcohol into a halogen, and then you do any of the reactions the halogen is capable of so that you can take it to the next step. And Jason asks, how do you know what is the product of the reaction, such as addition, substitution, alkyl shift, or hydration? I'm not sure I understand the question. So what I'm looking at when trying to figure out the product is I look at the reagent and I try to understand what is going to happen. So in this case, I know that I have H2SO4 in an aqueous solution. I know that the chlorine will leave, and then I ask myself, what happens next? I know that water can attack, but in a hot situation, it's going to favor elimination. In the previous reaction, I know that the halogens will come in and do a substitution. So it's really important that you understand how each of the reactions work so that when you look at it, even though you're not drawing out the entire mechanism, you still recognize this is the reaction I studied. This is what's going to happen as a result. Let me know if that answered your question, and then we'll move on to oxidation. With oxidation, we're talking about electrons, but in organic chemistry, especially in the topic we're looking at now, we're not looking at electrons. We're trying to figure out oxygen and alcohols and bonds to oxygen. So how do we make sense of this if we're just looking at electrons? I want you to take a step back and remember that a hydrogen atom is really just made of one proton and one electron. A proton and electron together make a hydrogen atom. And so if we look at the definitions again, let me move this down, then we can say that the loss of hydrogen is oxidation and the gain of hydrogen is reduction. But again, we're dealing with alcohol, so what does this have to do? Very simple. Hydrogen and oxygen are opposites. So anytime I lose a hydrogen atom, I will gain a bond specifically to oxygen. And if I gain a hydrogen atom, then I will lose a bond to oxygen. And I am very specific here in calling it bond rather than atom, because I want to show you exactly what is happening when we're looking at oxidation and reduction. Remember, we talked about 3 different types of alcohols. We did primary, secondary, and tertiary. So let's take a look what happens in each situation. We'll start out with a primary alcohol. And that is an alcohol sitting on a primary carbon, only one other bond to carbon. That's how I know it's primary. I can oxidize this thing twice, because if you look at the carbon that is holding the alcohol, let's just keep the primary here, I have a hydrogen here and a hydrogen here. In order to do oxidation, remember Leo the lion says, Gur, loss of electron oxidation, loss of hydrogen is oxidation. If I remove the first hydrogen atom, I get my first oxidation, and I'll just put O in a bracket to show you oxidation. This will give me the OH, or the oxygen is still there, one hydrogen is still there, but instead of adding an oxygen, I'm only adding a bond to oxygen. Notice that this bond goes to the oxygen that is already there, but now I have a pi bond, a double bond, rather than the single bond that I started with. I still have a hydrogen atom though, and so I can do a second round of oxidation. And in that second round of oxidation, I replace that second hydrogen with, in this case, an oxygen. And I happen to put a different hydrogen onto it. So it's not the hydrogen I started with, it's just another hydrogen. Notice that we went from 1 bond to oxygen, 2 bonds to oxygen, and 3 bonds to oxygen. The one on the right is most oxidized, and the one on the left is least oxidized or most reduced. If I start with a secondary alcohol, then the reaction is going to be very different. Well, it's going to be very similar, except I can't go all the way. So let's take a look. But first we have a question. Can you also cut it from the second carbon? I'm not sure I understand. Are you asking if I can take a hydrogen from here and put an alcohol there? That would be a very different reaction. So what I'm looking at here is simply increasing the number of bonds to oxygen on the carbon that already has an oxygen. In the case of my secondary alcohol, I only have 1 hydrogen atom. And so that means I can only do 1 round of oxidation unless I completely destroy the molecule and put an oxygen in. That's a much more advanced reaction that some students will learn. But for right now, this is as far as it goes with oxidation. And what we get here, just to clarify, is a primary alcohol will be partially oxidized to an aldehyde, which is a terminal functional group, and fully oxidized to a carboxylic acid. A secondary alcohol will only get oxidized to a ketone, and it cannot go any further. Question. The ethyl Grignard is a different reaction. It's not related to redox. It's a different reaction that can take advantage of these carbonyls. The last type of alcohol that we had looked at is a tertiary alcohol, and that is an oxygen sitting on a carbon that has 3 bonds to carbon. Notice that the tertiary oxygen, the tertiary alcohol, does not have any hydrogens to remove. I cannot remove them, and that means if I try to do an oxidation reaction, I will get nothing. No reaction, because there is no hydrogen to remove. I have nothing that I can react here. So these are the different types of oxidation. Let me know if you have any questions on this. And let's take a look at the reagents. What are the reagents that will do an oxidation, that will carry out the oxidation reaction? we have two classes of reagents to consider. We have the strong oxidizing reagents. I'll call Ox for oxidizing. And you should memorize these, but I want you to pay attention to what's in here. So you may see KMNO4, H2CrO4, Na2Cr2O7. You'll see a lot of different versions of this kind of reagent with the chromium, for example. But I want you to notice a pattern here: oxygen, oxygen, oxygen. The oxidizing reagents have lots of oxygen, and that is how I want you to recognize that this is an oxidation reaction. I have seen students tell me reduction when they see this. No, no, no. Oxidation, lots of oxygen. Reduction, no lots of oxygen. A strong oxidizing reagent will take the secondary alcohol to a ketone, and the primary alcohol will go all the way to a carboxylic acid. It does not stop at the intermediate, at the aldehyde. If you want to stop at the aldehyde, you have to use a very specific reagent. You have to use a weak reagent. For example, PCC. PCC stands for pyridinium chlorochromate. ACS students, you do have to memorize this. And the way that you can remember this, PCC is just one example. There's a couple more, but this is the one that you should memorize. PCC, think of it as a prude. It does not go all the way, and therefore it stops at the aldehyde, where any other oxidation reagent is going to take it all the way from the alcohol to the carboxylic acid. So let me know if you have any questions on this. And then let's go back here and look at this from a different perspective. If I can take a molecule and oxidize it all the way to an alcohol, I should be able to take the same thing and reverse it to go all the way, oxidize it from an alcohol all the way to a carbonyl, either a carboxylic acid or a ketone. If I do the reverse, that would be a reduction reaction. So I can reduce my carboxylic acid to an aldehyde. I can reduce my aldehyde to an alcohol, and I can also reduce the ketone to an alcohol. Since this is the alcohol chapter, let's specifically look at the reduction to get an alcohol. And with these reduction reactions, let me just pull this down a little bit. With the reduction reactions, if I have a ketone, which is a carbonyl in the middle of the molecule, I can reduce this ketone to get, here's the trick for it. You break the pi bond, you put a hydrogen here, and you put a hydrogen here, like that. So that will give you an O with an H. If I have an aldehyde, that is a very similar looking molecule, but it's got a terminal carbonyl, I subject this to reduction, same trick. Break the pi bond, put a hydrogen, and that gives me the alcohol with the hydrogen that I just added, the hydrogen that I had here, and now the hydrogen that I'm adding. So what we're doing here is going from a ketone to a primary alcohol, and the aldehyde, a ketone is not primary because that is most definitely secondary. A ketone goes to secondary and the aldehyde goes to a primary alcohol. Question. So PCC will work with primary, giving us an aldehyde. Yes, PCC will take any alcohol and give it one pi bond. I'm holding up two fingers. One pi bond. So if you look over here, I can also use PCC to go from a secondary alcohol to a ketone, because a ketone is one pi bond. So the distinction is most important if I want to stop at the aldehyde, but PCC will also give me the ketone if you're trying to remember, okay, how do I get a carbonyl in there? Aldehyde ketone doesn't matter. You can use PCC in either case. Let me know if that answers your question. And a reminder for a copy of the session notes along with my alcohol reactions practice worksheet, go to layitforsci.com/orgolive and I will email it to you. Whether you're watching live or the recording, it will be an automatic email with the information so that you can get right to practicing. If you're watching live, I have to finish the session first so I can send it to you, but then afterwards. The reagents that will carry out reduction. If oxidation had a lot of oxygen, what do you expect to see in a reduction reagent? Well, if we're adding hydrogen, we expect to see a lot of hydrogens. And the two that you are most commonly going to see to carry out this reaction include NaBH4 and LiAlH4. Lithium aluminum hydride and sodium borohydride in a mild acid workup, because when the reaction takes place, and I have a YouTube video that shows you the mechanism, you get an O minus, and then the mild acid is going to protonate so that you can have a neutral alcohol. When you study sodium borohydride and lithium aluminum hydride, you're going to learn that one is weaker and one is stronger, which matters when you're dealing with a more advanced reactions. But for the sake of alcohols from ketones or aldehyde, you can use both reagents interchangeably, and they're going to give you the same exact reaction, the same exact product. So let me know if you have any questions on this so far. Do those reagents go together? No. So these are two different reagents. Let me correct it. Instead of saying and, I will put or. And that means if I'm showing a reaction, then it would look something like this. Say I'm trying to do a reaction of this molecule right here, and I react it with NaBH4 as step 1 and step 2, H2O. I look at my molecule. I recognize that I have a carbonyl. The trick here is you break the bond. You put a hydrogen here, and then you just redraw the skeleton as you see it, which in my case, I copied everything. So let's remove all that. The skeleton has one bond to oxygen. We now add in those two gray hydrogens, one here and one here. But really in line structure, that hydrogen is not necessary. And so there we go. That is my reaction. I have a ketone in this case. I reacted it with NaBH4. Then I reacted it with a mild acid workup. H2O is often shown just as it is. And the product is an alcohol at the position that used to have a carbonyl. Question. Do the hydrides have to be lithium and sodium salts? Why can't we have potassium or something? I have no idea. I haven't thought about this before. What we're really looking at here is a spectator ion with a BH4 minus, an ALH4 minus. And so it shouldn't matter what the spectator salt is, what the spectator cation is, but I don't know. That is a very, very good question. If anyone knows the answer, go ahead and type it in, because now I'm curious as well. So let's jump on over to the Grignard. This came in by popular request to please cover the Grignard reaction. The Grignard is one of my go-to methods when working in synthesis and trying to create a longer carbon chain. The way this works is I have an alkyl halide. Let's go with something simple to start, something like a CH3Br. I react it with magnesium in an ether, because ether is not going to react with the Grignard. And what will happen here is the Grignard is going to insert itself as a magnesium in between the carbon and the halogen. This makes the carbon very, very reactive. This is going to be carbanion-like. And this is an ideal reagent to attack a carbonyl. So for example, if I have, let's start simple, I have a ketone and I react it with this Grignard, a CH3MgBr. What'll happen is the carbon, acting like a carbanion from this bond right there, is going to attack the carbonyl and kick up those pi electrons so that the oxygen now has a negative charge. What I'm left with is the two carbons that I started with on my carbonyl, so the initial carbon chain. Oxygen now has a negative charge, and then I have the methyl that came in from the attack attached right here. I just grew the carbon chain. The Grignard salt sticks around, but we don't have to show it unless your professor asks for it. In the final step, we want to add acid. Just make sure you're adding it as a separate step and not into the Grignard, because that'll destroy the Grignard. This is going to protonate the O- to give me an alcohol. So what I want you to notice here is that the Grignard reaction, the key with the Grignard reaction is that we can take a carbon chain that has a carbonyl and I can add two things to it at the same time. One, I can grow the chain, and two, I can turn a carbonyl into an alcohol. And this is really, really important because in synthesis, you're always looking to grow your chains longer. We have a question on the last one. Dibal is also considered mild. Yes. So dibal, when you have your carboxylic acid derivatives, you're going to learn a lot more about the difference between reducing reagents, and that's typically where dibal will show up. So going back to here, the Grignard is used to grow the carbon chain. So let me show you one more, and this time without the mechanism. Say I have a molecule that looks like this. And I have an aldehyde at the end. I want to grow the carbon chain, and I also want to put an alcohol onto this molecule. What I will do is introduce a Grignard, and let's go with something bigger this time. Let's say I have something like this with an MgCl. Here is the shortcut to come up with a product. First, redraw your skeleton exactly as you see it. Where you have a carbonyl, only draw one bond to oxygen and put a hydrogen there. At the carbonyl carbon, put a brand new bond, and then whatever is attached to the Grignard gets attached over there. In this case, I have 1, 2, 3 carbons, 1, 2, 3 carbons with a methyl group branching on the second to last carbon. And there's my product. Make sure you put step 1 and then step 2, H3O+, that's what gave us the alcohol from the O- intermediate. Question, where did the methyl go in the last structure? Oh, it disappeared is where it went. The methyl should be right here. Good catch. Thank you. Does the type of OH formed dependent on the carbonyl group used? Yes, absolutely. Notice that in this reaction, I started with an aldehyde, and the product is a secondary alcohol. What if I did a very similar reaction? So let's copy it exactly as is. But this time, instead of starting with an aldehyde, let's make a ketone. So all I do is make this a little bit longer. Let's do that. For my product, I start with my carbon chain exactly as I see it. The carbonyl, I break a pi bond and only put an O with an H. That's my alcohol. A new bond starting at the carbonyl carbon, and then I add the incoming Grignard, in this case 1, 2, 3, with a methyl group right there. So notice that for the one I started here, I started with an aldehyde plus a Grignard, in this case gave me a secondary alcohol. When I started with a ketone and attacked it with a Grignard, I got a tertiary alcohol because I started more substituted and therefore the product is also more substituted. Okay, really good question. Let me know if that helps. The red line came from where? Did it come from the isopropyl attached to the MgCl? Yes, the red line represents the electrons that form the bond between the incoming group and the carbonyl. So if we go back to the mechanism, the electrons between carbon and magnesium, those are the electrons that do the attack. So you see how I have it here forming an attack? That would be these electrons right there forming that new bond, connecting those two. I want to show you a trick with these molecules. So let's say you're given something like this for synthesis, but you're actually starting with the product. So you're given an alcohol and you are asked to figure out where it came from. Here is the trick. If you recognize that you have a synthesis reaction where you have an alcohol on a carbon that grew, or I should say a carbon chain that grew, what you want to do is identify the carbon holding the alcohol, and that right there is your carbonyl carbon, and then you can break it. And you can say the Grignard either came from here or from here. I have two different options that I could have used to synthesize this one. So let me show you both, because if this comes up in synthesis, I want you to be able to catch it no matter what. If I do the line that I drew on the right, then this whole thing is one molecule. And we already saw that, but I'll try it again. I copy it exactly as I see it, and then I have this right here, but I turn the carbonyl into a pi bond. The other half of the molecule, I turn into a Grignard. So I will say plus, and because it's an aldehyde, I'll add the hydrogen there, plus, I redraw the other portion exactly as I see it, and then I add an Mg halogen, Mgx. It could be MgCl, MgBr. That is one option. If I break it in the other direction, then I can break it like this, where that is my starting molecule. And that would be this portion right here. The oxygen, I add a pi bond, turn that into a carbonyl. And then this portion here is my Grignard, which means I'm reacting it with a benzene ring that has attached to it Mgx. If you like this shortcut, let me see a thumbs up in the comments. And then I'll show you the same thing for the tertiary alcohol. So we'll apply the same exact trick for the tertiary alcohol, except here we have quite a few options. So let's see. The carbon holding the alcohol, that is my carbonyl carbon. But the question is, what got attached? So I have the option of breaking it here, here, or here, and I can have 3 different starting molecules for this reaction. Let me show you. Option 1 will take this as the incoming group. That right there could have been my ketone. That means I have my carbon chain as I see it. Attached to it, I have this right here. And let me actually keep the colors consistent so that you can follow, especially when you're downloading the notes. liveforsci.com/orgo live, you can download these notes. And I will have an O, but I turn that into a carbonyl. And I react it with this portion, which means I have, exactly as I see it, with an Mgx. That's option number 1. Option number 2, my Grignard is going to be this one. And that means this whole thing is my starting molecule. So that would look like this. I have my ring attached to that. I have this one right here. and then I have where I show the red bond, and then I have all this as one starting molecule. This is my oxygen where I see it, but I turn it into a carbonyl. And then my Grignard is simply an ethyl bound to an MgX. That's option number 2. And then option number 3, because we have a tertiary, that means I have 3 different options. I already used that one and that one, so I can do this one right here as my Grignard. That means this one right here is my starting molecule. What does that look like? For the starting molecule, I have this right here with the oxygen that I turn into a carbonyl. Okay, I'm going to have to twist this a little bit. So I'm going to put that same oxygen down here as a carbonyl. And then I'll add the red bond here with that purple group attached to it. So it looks a little bit wonky, but if you count your carbons, you'll see that this is exactly what I have on here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I just drew it a little bit twisted. And then the Grignard portion, that is right here with just an MgX. Let me know if you found this helpful, because we took quite a detour on this shortcut. Do you see this saving you any time on your upcoming synthesis questions? Question, can you explain more substituted and less substituted? I don't remember where you typed that. I assume you're talking about the secondary and tertiary, or was it with the aldehyde and ketone? The aldehyde is a carbonyl. Whoops, did not mean to erase that. The aldehyde is a carbonyl that only has 1 R group attached to it. The ketone has 2 R groups attached to it. So if we then look at the resulting alcohol, the alcohol has 2 R groups attached to it because it got an extra one. This alcohol has 1, 2, 3 R groups attached to it because the ketone had more R groups to begin with, and so does the product. Does the positioning of MGBr in a reaction significantly impact the outcome? I'm not sure I understand your question about the positioning of the MgCl. It's really a matter of wherever the MgCl is attached, that is the reactive carbon, and it simply determines what the chain looks like, meaning where the branches and carbons and bonds are coming from. What if I give you a molecule that looks like this? So I have a carbonyl right here and an oxygen right here. And I want to react it with an isopropyl Grignard MgCl. If we use the shortcut that I showed you, then you would imagine that you break the pi bond, you redraw the carbon skeleton as you see it. Everything should ideally remain intact. You have the OH right here, and then you would expect to get this right here. This looks like what we want to happen, except this is not going to happen. The reason this isn't going to happen is because the Grignard is very reactive in the presence of a protic group. This alcohol right here will destroy the Grignard, and then we will have absolutely no reaction happening. So if I want to carry out this reaction, what I have to do is turn the alcohol into something that is not an alcohol, that does not have a protic group. And if I can protect it, if I can hide that alcohol, the Grignard won't see it, and the Grignard will react the way we want it to. One protecting group that you should know is the silyl ether, which we're going to simplify simply as, we're going to write it as TMS, that's the silyl ether portion, with a chlorine. Similar to when we used the toluene sulfonyl chloride, the chloride was just a leaving group to help put a big group on the molecule. Same exact thing is happening here. The carbonyl is untouched, but the alcohol is no longer an alcohol, it is now an ether. bound to TMS. The Grignard will not attack the ether. The Grignard now will only attack the carbonyl, which is what we're looking for. This will give me the kind of reaction that I was hoping for, where the pi bond breaks. I get an oxygen right here with a hydrogen added. I have the new group that should be, I'll show red for the new bond, and then the isopropyl group being added. The alcohol is still protected with the TMS group. And now what I do is simply remove that protecting group using something like F-, and I get the product I was looking for. So really what I need to cross out here is this. Instead of going this way, I simply go this way. Again, what I'm doing here is saying if the Grignard is going to attack the alcohol, what if I make the alcohol invisible to the Grignard by just putting a protecting group on it? Remember when I showed you how to create the Grignard? I said we're going to use an ether because the ether is not reactive. The silyl ether is a perfect example of something that is not reactive. And that ether is going to protect the alcohol. Then I do my reaction. I remove it, and I get the product I'm looking for, which in this case is two completely different alcohols. One that we started with, and one that we're getting from the tertiary alcohol. Depending on what your professor specifically focuses on, there are many, many different alcohol reactions that you have to learn and lots more to practice. So I have a practice worksheet for you that you can get for free. Just go to my website, leahforsyth.com/orgoalive and sign up there. When you sign up, you're going to get a copy of today's session notes, today's worksheet, as well as all the other live streams on this channel. You'll get those session notes and those worksheets so that you can practice all the different topics. If you're looking for even more help, if you're looking for me to teach you all of Organic Chemistry 1 and all of Organic Chemistry 2, as well as you're going through the material, if you have questions, if you want me to answer your specific questions on a regular basis, you study, you have a question, you get stuck, you want help, that's what the Organic Chemistry Study Hall is all about. So this is a group where you get to work with me. You get to watch my entire video library. You'll have access to the entire Orgo 1 and Orgo 2 video library. Not what I have on YouTube, but a lot more in-depth, lots more practice, video solutions, step-by-step explanations, all the quizzes on my website, as well as the tutoring and support group where you can post questions every single day. My computer's trying to die on me. You can post questions every single day to get help with anything you're working on. Go to leahforsyth.com/join where you can sign up and you can get started right away.